Imagine teaching a computer by showing it examples, like pictures of cats, until it learns to recognize new ones on its own. This is supervised machine learning, and in this course, we'll break it down simply, using real-world analogies and visuals, so you can understand how machines learn from data. Supervised learning means teaching a machine by example, giving it inputs and the correct outputs, like showing a child fruit and naming each one. The machine learns to map inputs to outputs by checking its predictions against the true answers, refining itself with every example. Supervised learning powers predictions everywhere, from spam filters to medical diagnoses, by learning from labeled data to make smart guesses about new information. It's a universal tool for turning past data into future insights, shaping the technology we use every day. Every time your email filters spam, your shopping site recommends products, or your map app predicts travel time, supervised learning is working behind the scenes. Even face recognition in photo apps relies on models trained with labeled examples to make your digital life easier. Unlike traditional programming with rigid rules, supervised learning lets machines discover patterns by learning from labeled examples, like recognizing handwritten digits or identifying spam. The quality of a model depends on the quality and quantity of examples it's given. Good data leads to smart machines. Supervised learning solves two main types of problems: classification, predicting categories like spam or not spam, and regression, predicting numbers like house prices. Knowing whether you need a label or a number is the first step to building the right machine learning model. To build machine learning models, we need to speak the language of data. It revolves around three key concepts: inputs, outputs, and labels. Inputs are the information we give to the model. Outputs are the predictions the model makes. Labels are the correct answers used to teach the model. Let's use house price prediction as an example. The inputs or features include square footage, number of bedrooms, bathrooms, age, and zip code. The output is the predicted selling price. The label is the actual selling price. We use inputs and labels to train the model. Once trained, we give it new inputs to get predicted outputs. Now that we have established a solid foundational understanding, let's look at the road ahead. This course is structured to take you step by step from basic concepts to building and evaluating your own supervised learning models. First, we'll dive into data, then the algorithms themselves, like linear regression and decision trees. We will cover training, testing, and validation. Finally, we will bring everything together and cover the key metrics used to evaluate model performance. A common question people have when approaching a topic like machine learning is, do I need to be a math wizard or a programming prodigy to understand this? Let me set your mind at ease right now. The answer is no. This course has been designed from the ground up for beginners. You do not need any prior experience in machine learning, artificial intelligence, or data science. We are starting from square one, and our primary goal is to build intuition. The focus will always be on the why and the how in a conceptual sense, not on dense mathematical proofs or complex code libraries. We believe that the core ideas of supervised learning are accessible to everyone. They are based on logic and patterns that we can all appreciate. While advanced machine learning does involve deep mathematics like linear algebra, calculus, and probability theory, we will touch upon these concepts only at a high intuitive level. We will use visuals to represent these ideas rather than getting bogged down in the symbolic notation. Think of it as learning the physics of how a car works, understanding the engine, the wheels, the steering, without needing to be a mechanical engineer who can build one from scratch. The same goes for programming. While we will have a practical coding example later in the course to show you how these ideas are implemented, the goal of that section is to demonstrate the process, not to teach you how to become an expert coder. The code will be kept simple and will be explained line by line. Your main takeaway should be the workflow and the logic, not the specific syntax of a programming language. If you are already a programmer, that's great, but it is by no means a prerequisite for gaining a deep and valuable understanding from this course. All you need to bring with you is your curiosity and a willingness to think about problems in a new way. Our approach is to make learning an engaging and illuminating experience. We will use short, digestible sections, clear language, and helpful analogies to guide you. So, relax, get comfortable, and prepare to unlock the fascinating world of supervised machine learning. We are about to embark on a journey that will change the way you see data, technology, and the potential of intelligent machines. Let's get started. Everything in supervised machine learning begins and ends with data. It is the fundamental ingredient, the fuel from which our intelligent models grow. The model scrutinizes this data, searching for patterns. The quality, quantity, and relevance of this data will ultimately define the limits of what our model can achieve. It is the single most important factor in the entire process. This complete reliance on data is what separates machine learning from traditional programming. Here the data takes center stage. Data scientists often spend up to 80% of their time simply collecting, cleaning, and preparing data. It is the lifeblood that powers every prediction, every classification, and every insight we hope to generate. Features are measurable properties or characteristics. They are the building blocks of input data, helping models make decisions. For a house, features include square footage, bedrooms, and age. For email spam detection, features might be capitalized words or sender domain. Think of features as spreadsheet columns. This is how a machine sees the world. Choosing the right features is key. What contains signal, not just noise? Engineered features can provide more predictive power than raw data. Models are only as good as the information given. Every input is broken down into features. The model learns to weigh these features. Features describe the problem to the machine. If features are the questions, then labels are the answers we want the model to learn. In supervised learning, our dataset must contain these labels. The goal is for the model to learn the relationship between the features and the labels. In a house price dataset, each house's features has a corresponding label, the actual sale price. Creating these labels can be simple or complex. It is absolutely essential for high-quality training data. Without labels, we have no way of knowing if our model is learning correctly, like a student with no answer key. The ground truth anchors the entire learning process in reality. So we have our features, the inputs, and our labels, the outputs. How do we organize them for a machine to use? We combine them into a dataset. A dataset is simply a structured collection of examples. The most common way to think about a dataset is as a single table or spreadsheet. Each row in this table represents one complete example, also known as a data point, a sample, or an observation. Each column represents either a feature or the label. This clean tabular structure is the standard format that nearly all machine learning algorithms are designed to work with. Let's visualize this for a simple problem: predicting whether a student will pass an exam based on how many hours they studied and how many hours they slept the night before. Our dataset would be a table. Each row would represent a different student. The first column might be hours studied. That's feature 1. The second column would be hours slept. Feature 2. The final column would be the result we want to predict: passed exam, the label, which could be a yes or a no. A single row might look like 8 hours studied, 7 hours slept, yes. The size of this dataset is crucial. A model's ability to generalize, to perform well on new unseen data, depends heavily on the number and diversity of examples it has been trained on. If we only train our student pass model on 10 examples, it might not learn a very reliable pattern. If we train it on 10,000 examples of students with a wide range of study and sleep habits, it will develop a much more robust and accurate understanding of the relationship between these features and the outcome. More high-quality data is almost always better. This complete collection of rows with both features and labels is our training dataset. It is the textbook from which our algorithm will study. During the training phase, the algorithm will comb through this table row by row, example by example, continuously refining its internal formula for predicting the label from the features. The structure of this dataset, rows as individual examples, columns as attributes, is a fundamental concept. Before any learning can happen, we must first gather our information and carefully organize it into this clean, machine-readable format. Machine learning algorithms understand numbers, not concepts. Our job is to translate the real world into numerical language. This is feature engineering, selecting the right features and converting them into a suitable numerical format. Consider a house's location. We need to convert these concepts into numbers, like kilometers to the city center. This is also necessary for categorical data. A common technique is one-hot encoding, where we create a new binary feature for each category. Even text data needs to be converted into numbers. Feature engineering is a critical, creative step. Data is essential, but quality trumps quantity. Garbage in, garbage out is machine learning's first commandment. Flawed data yields flawed predictions, regardless of the algorithm's sophistication. Good data is accurate, clean, relevant, and representative. Crucially, it must be unbiased. Addressing bias is a major ethical challenge, requiring careful data origin examination for a fair, equitable world. Supervised learning algorithms learn a mapping, a mathematical function connecting input features to an output label. Think of this mapping as a recipe. The inputs are ingredients, and the output is the finished cake. Imagine a house's price determined by square footage. The algorithm learns from house data, adjusting its rule until it accurately predicts prices. This iterative process is the essence of training. This learned mapping is the model. Supervised learning uses data to discover the hidden mapping between what we know and what we want to predict. Let's zoom in on the data used for one of the two main types of supervised learning classification. As we discussed, classification is all about predicting a discrete category. The label in a classification dataset is not a number on a continuous scale, but rather one of a finite set of classes. The data is structured to help the model learn how to draw boundaries between these different classes. The goal is to learn a mapping that takes a new data point's features and correctly places it into the right category or bucket. Consider the classic problem of identifying handwritten digits from 0 to 9. This is a multi-class classification problem because there are 10 possible output classes. The training data would consist of thousands of images of handwritten digits. Each image is broken down into features, perhaps the pixel values. Each image also has a label, the actual number it represents, 0, 1, 2, and so on. The model's task is to look at the pixel features and learn what makes a 7 look like a 7 and not a 1. It learns the visual patterns that define each distinct category. The data for a binary classification problem, which has only 2 possible output classes, is structured similarly. For our spam filter, the label for each email is either spam or not spam. For a medical diagnosis model, the label might be disease present or disease absent. The algorithm learns a decision boundary. For any new data point, it checks which side of the boundary its features fall on. If it's on one side, it's classified as spam. If it's on the other, it's not spam. The training data is used to find the optimal location for this boundary. When preparing data for classification, it's important to have a balanced number of examples for each class, if possible. If you train a model to detect a rare disease using a dataset where 99.9% of the examples are disease absent, the model might learn a lazy strategy. Just predict disease absent every time, and it will be 99.9% accurate. While accurate, this model is useless for its intended purpose. Therefore, handling class imbalance in the dataset is a common and important challenge when dealing with classification problems. The structure and balance of your categorical data directly shape the model's decision-making ability. Now let's turn our attention to the data used for the other major type of supervised learning, regression. Regression is all about predicting a continuous numerical value. The label in a regression dataset is not a category, but a real number. It could be a price, a temperature, a distance, or, any other quantity. The data is structured to help the model learn the trend or the functional relationship between the input features and this continuous output. The goal is to learn a mapping that can predict a specific point on a numerical spectrum. Our house price prediction problem is the quintessential example. The label for each house in our dataset is its selling price, a number like $451,200 or $623,500. The features are other numbers like square footage and age. The regression algorithm's job is not to draw a boundary between classes, but to fit a line or a curve that gets as close as possible to all the data points. It's really trying to capture the underlying trend. For example, it will likely learn that as the square footage feature increases, the price label also tends to increase. Another example could be predicting a person's weight based on their height. Our dataset would have 2 columns, height as the feature and weight as the label. Each row would be a different person. The regression model would study this data to find the mathematical relationship between height and weight. The resulting model might be a simple formula like predicted weight equals some number times height plus another number. This learned formula can then be used to estimate the weight of a new person, given only their height. When preparing data for regression, it's important to look at the distribution of your features and labels. Are there extreme outliers? For instance, a single billion-dollar mansion in a dataset of normal suburban homes could heavily skew the model's learning process, pulling the regression line too high for all the other houses. Identifying and handling such outliers is a key step in preparing regression data. The goal is to provide the model with a clean set of examples that accurately reflect the central trend you want it to learn. If there is one single idea to take away from this entire discussion of data and labels, it is this. Your data sets the ultimate performance limit for your model. It defines the ceiling. You can have the most powerful state-of-the-art algorithm, but it can never perform better than the quality of the data it is trained on allows. A brilliant student cannot ace a test if their textbook is full of errors and missing pages. In the same way, a brilliant algorithm cannot make accurate predictions if its training data is flawed. This means that the path to a better model often lies not in finding a more complex algorithm, but in improving the data itself. This could mean collecting more data to better represent the real world. It could mean spending more time cleaning the data to remove errors and inconsistencies. Most powerfully, it often means feature engineering, creating new, more informative features that reveal the underlying patterns more clearly to the algorithm. A single, well-crafted feature can be worth more than 1,000 new rows of mediocre data. This principle has profound implications for how we should approach machine learning projects. It tells us to be humble about our algorithms and obsessive about our data. Before trying to build a complex deep learning model, first ask, is my data clean? Are my labels accurate? Are there more relevant features I could be using? Have I addressed potential biases in my dataset? Answering these questions and acting on them will almost always yield a bigger improvement in performance than simply switching to a more advanced algorithm. So, as you continue your journey into supervised learning, always remember this golden rule. The model is a reflection of the data it was shown. The patterns it finds, the predictions it makes, and the biases it holds are all inherited directly from its training examples. The best practitioners are not those who know the most algorithms, but those who best understand their data. By mastering the art of collecting, cleaning, and shaping data, you are building the strong foundation upon which all successful machine learning models are built. Now that we understand data, it's time to open the toolbox and explore machine learning algorithms. Algorithms are the engines that learn. An algorithm is a procedure that takes a dataset and produces a trained model. Think of them as tools. Some algorithms are for regression, others for classification. We'll explore fundamental algorithms, focusing on visual and intuitive understanding. We start with linear regression and build to more sophisticated methods. The goal is to build a mental model for each algorithm, empowering you to reason about your models. Let's begin. Let's start with linear regression, the foundation for many complex methods. It's used for regression tasks, predicting continuous numerical values. The core idea is that a straight line best describes the relationship between inputs and outputs. The algorithm's goal is to find the single straight line that best fits the data. For example, predicting salary based on experience. Linear regression looks at the data points and draws the best straight line through them. This line of best fit captures the data's trend. To predict, find the experience on the x-axis, go up to the line, and read the salary on the y-axis. It summarizes the relationship with a clear trend line. Linear regression learns through optimization, minimizing errors between predicted and actual values. The algorithm adjusts the line's slope, m, and y-intercept, b, to reduce the cost function, which measures the sum of squared errors. Gradient descent helps find the minimum cost by iteratively taking steps down the cost function's slope, until it converges on the optimal m and b values. Linear regression is powerful, but the world isn't always linear. Sometimes relationships follow a curve. This is where polynomial regression comes in. It fits curves to data. The magic lies in feature engineering. We start with a feature, x, and create new features by raising x to higher powers, like x squared, x cubed, and so on. Even though we are fitting a curve, the underlying algorithm is still linear regression. However, it is very easy to overfit. It will perform terribly on new data. Finding the right balance between simplicity and complexity is key. Let's switch gears from regression to classification and explore decision trees. This algorithm is intuitive and easy to understand. A decision tree predicts a target variable by learning simple decision rules from data features. It's a flowchart-like structure where each node represents a feature test, each branch represents the test outcome, and each leaf node represents a class label. Imagine diagnosing a patient. Does the patient have a fever? A cough? This path of questions leads to a final decision. That's how a decision tree works. The algorithm learns the optimal questions from training data, finding the best question to ask first. The best question splits the data into pure groups. Decision trees learn by asking the best question at each step. But how do we mathematically define best? The core concept is purity. A pure group has data points belonging to the same class. Algorithms use metrics like Gini impurity or entropy to measure this. The goal is to make splits that decrease the impurity score, resulting in the largest information gain. This process repeats recursively, splitting data into branches until a stopping condition is met. Decision trees are interpretable, but prone to overfitting. Random forests combat this. Instead of one complex tree, it uses many simple trees. It combines their predictions. The random part is key. Randomness is introduced in two ways: data sampling and feature selection. This creates a diverse set of experts. This diversity makes the random forest robust and resistant to overfitting. Let us explore support vector machines, or SVMs, primarily used for classification. The core idea is to find the best line, or hyperplane, that separates data points of one class from another. The best separating line maximizes the distance from the nearest data points of each class. The data points closest to the separating hyperplane are called support vectors. The SVM's elegance lies in its goal: find the widest possible street between classes. The idea of finding a maximum margin hyperplane is great for data that is linearly separable, meaning you can draw a single straight line to separate the classes. But what happens when you cannot? Imagine a dataset where the red dots form a circle in the center of a plot, and the blue dots are scattered all around them. There is no straight line you can draw in 2 dimensions that will successfully separate the two classes. This is where the true power of SVMs comes into play, through a brilliant mathematical technique known as the kernel trick. The kernel trick is a way of dealing with non-linearly separable data by cleverly projecting it into a higher dimensional space, where it does become linearly separable. This sounds very abstract, but we can build an intuition for it. Imagine you have a flat sheet of paper, a 2-dimensional space, with red and blue dots mixed together. Now imagine you could somehow bend or warp that paper, lifting the red dots up into a 3rd dimension. From this new higher dimensional perspective, you might be able to slide a flat sheet, a 2-dimensional plane, in between the lifted red dots and the blue dots that remained on the original level. This is what the kernel trick does, but with mathematics instead of physical warping. A kernel function takes our original low-dimensional data and calculates what the relationships between the data points would look like in a higher dimensional space, without ever actually having to compute the new coordinates. This is incredibly efficient. It allows the SVM algorithm to operate in a very high-dimensional feature space, finding a linear separating hyperplane there, while all the computations are done in the original, lower-dimensional space. It gives us the power of high dimensions without the computational cost. Common kernel functions include the polynomial kernel, which is related to polynomial regression, and the radial basis function, or RBF kernel, which is extremely powerful and can handle very complex relationships. The RBF kernel essentially maps the data into an infinite dimensional space. By using these kernels, SVMs can learn incredibly complex, non-linear decision boundaries. They can draw circles, curves, and all sorts of intricate shapes to separate the classes. The kernel trick is what transforms the simple SVM from a linear classifier into a highly flexible and powerful modeling tool. Despite its name, logistic regression is a fundamental algorithm for classification. It's the go-to method for binary classification problems, like yes or no. The core idea is to take the output of a linear equation and squash it into a range between 0 and 1. This squashed value can be interpreted as a probability. Logistic regression feeds the score into the sigmoid function, which has a characteristic S-shape. It takes any input value and squashes it onto a scale between 0 and 1. We can then set a decision threshold. If the predicted probability is greater than 0.5, we classify it as class 1, otherwise, class 0. An optimization algorithm finds the best set of weights for the input features. Because of its simplicity and interpretable probabilities, logistic regression is often a first choice for classification problems. We've now toured several key algorithms: linear and polynomial regression for predicting numbers, and decision trees, random forests, SVMs, and logistic regression for predicting categories. So, a natural question comes up: which one is the best? Well, the honest and honestly the most important answer in machine learning is, it depends. There is no single algorithm that is always the best performer for every problem. This is actually such a central concept in the field that it has a name: the no free lunch theorem. It basically states that no one model works best for every possible problem. The choice of algorithm depends on a huge number of factors. The size and dimensionality of your dataset is a major one. Some algorithms, like SVMs, can be pretty slow to train on very large datasets with lots of examples. The interpretability of the model is another key consideration. If you need to be able to explain exactly why your model made a particular prediction, for example in a medical or legal context, a simple decision tree or a logistic regression model is far more transparent than a complex random forest or a kernelized SVM, which can really feel like black boxes. The underlying structure of your data also matters. If you have strong reason to believe that the relationship between your features and your output is linear, then linear or logistic regression is a great, simple starting point. If the decision boundary is likely to be very complex and non-linear, a random forest or an SVM with an RBF kernel might be more powerful. Often, honestly, the best course of action is just to experiment. Data scientists will frequently train several different types of models and compare their performance on the same validation dataset to see which one works best for their specific problem. The journey of choosing an algorithm is not about finding a single silver bullet. It's about understanding the trade-offs. There's a constant tension between model complexity and interpretability, between predictive power and computational speed, between flexibility and the risk of overfitting. A good data scientist doesn't just have a favorite algorithm, they have a well-stocked toolbox and a solid understanding of the strengths and weaknesses of each tool. They know how to select the right tool for the specific job they need to accomplish, based on the unique characteristics of the problem at hand. We have our data and algorithms, but here's the golden rule. Never evaluate your model's performance on the same data it was trained on. Why is this so critical? Testing on training data is a trap. Models can memorize data, giving a misleading sense of performance. Test on new data to truly measure ability. Split your dataset before training. Use one pile to train and the other to test. This split is fundamental to building a model. The training set is the largest portion of our data. This is the data we show to the algorithm. Think of the training set as the model's classroom. It is the collection of labeled examples that the algorithm will study. The model pores over every single data point in this set, adjusting its internal parameters to minimize its prediction errors. All the learning happens exclusively on this data. The size and quality of the training set are paramount. Therefore, we typically allocate the largest chunk of our data to the training set. During the training phase, the model is in a feedback loop with this data. After our model has completed its education in the classroom of the training set, it is time for the final exam. This is the role of the testing set. The testing set is a smaller portion of our original data, perhaps the remaining 20 or 30% that we have kept completely separate and untouched throughout the entire training process. The model has never seen a single data point from this set. The labels for the testing set are hidden from the model. It is the ultimate test of how well the model has learned to generalize to new unseen data. The process is straightforward. We take our fully trained model and feed it the input features from the testing set, one example at a time. For each example, the model makes a prediction. We then compare this prediction to the true label of that test example, which we have kept hidden. By comparing the model's predictions to the true labels across the entire testing set, we can calculate performance metrics like accuracy, precision, or error. This gives us our final, honest assessment of how the model is likely to perform in the real world. The score on the testing set is our bottom line result. It is the number we report to stakeholders to describe how good our model is. Because the model has never seen this data before, its performance here is a much more realistic measure of its capabilities. If a model achieves 98% accuracy on the training set, but only 70% accuracy on the testing set, we know we have a problem. The model has likely just memorized the training data and has not learned the underlying pattern. The testing set is our reality check. It is vital that the testing set is only used once, right at the very end of our project. If we use the testing set to help us tune the model, we are breaking the golden rule. The moment the test data influences our decisions about the model's design, it ceases to be a true, unbiased test. It becomes part of the training process, and we are back to fooling ourselves. The testing set must be treated as a locked vault, to be opened only when we have a final finished model that we are ready to evaluate once and for all. So, we have a dilemma. We need to train our model on the training set, and we can only use the testing set once at the very end. But in between, we need a way to make decisions. How do we choose which algorithm is best? For a decision tree, how do we choose the optimal depth? For an SVM, how do we choose the best kernel? These choices, known as hyperparameters, are settings that we, the data scientists, must choose before the training process even begins. We need a way to evaluate our model during development without touching the precious testing set. This is where a third data split comes into play. The validation set, sometimes called the development or dev set. The validation set acts as a practice test. It's a separate chunk of data that we peel off from our initial training data. So instead of a simple 80-20 train test split, we might do a 60/20/20 split. 60% of the data becomes the training set, 20% becomes the validation set, and the final 20% is locked away as the testing set. This three-way split is a standard best practice in machine learning. Here is how it works in practice. We pick an algorithm and a set of hyperparameters, for example, a decision tree with a maximum depth of 5. We train this model only on the training set. Then we evaluate its performance only on the validation set. We look at the score. Then we try a different set of hyperparameters, for example, a decision tree with a depth of 10. We train this new model, again only on the training set, and evaluate it on the validation set. We can repeat this process many times, trying different algorithms and different settings. The validation set gives us a reliable proxy for how our model might perform on unseen data. We can use the performance on the validation set to guide our choices. We choose the algorithm and hyperparameter settings that give us the best score on the validation data. This entire process of model selection and tuning happens using only the training and validation sets. The testing set remains untouched and unseen, waiting for its role as the final, unbiased judge of our chosen champion model. The validation set is the crucial intermediate step that lets us tune our model without cheating. Let's solidify our understanding of this crucial three-way data splitting strategy. The train-validate-test split is the bedrock of reliable model development. Each of the three sets has a very distinct and non-overlapping purpose, and honestly, using them correctly is essential for building a model you can trust. It prevents us from making overly optimistic claims and ensures that our final evaluation is as honest and realistic as possible. Let's review the specific role of each component in this workflow, imagining we are building a model to predict customer churn for a subscription service. First, we have the training set. This is the largest portion of our data, maybe around 60 to 70% of our customer records. This is the model's textbook. We feed this data, with both the customer features and the churned or not churned labels, directly to our learning algorithm. The algorithm studies these examples and learns the patterns associated with customers who cancel their subscriptions. The model's internal parameters are fitted and optimized exclusively using this data. The training set is for pure learning and nothing else. Next, we have the validation set. This is a smaller slice of the data, maybe 15% of our records. This is our practice exam. After training a candidate model on the training set, we use the validation set to see how it performs on data it wasn't trained on. We might test a logistic regression model and a random forest model and see which one gets a better score on this validation set. We might also use it to tune hyperparameters, like finding the optimal number of trees for our random forest. The validation set guides our decisions about model selection and configuration. Finally, we have the testing set, our remaining 15% of the data. This is the final sealed exam. After using the validation set to select our single best model, our champion, we bring out the testing set for one last evaluation. We run our chosen model on this data, which it has never seen at any point during training or tuning. The performance score on this testing set is our final reportable metric. It represents our best estimate of how the model will perform when deployed in the real world to predict churn for new customers. This strict separation of duties is non-negotiable for sound machine learning practice. Careful data splitting combats overfitting, where a model learns the training data too well. Instead of learning the underlying trend, it memorizes noise and irrelevant details specific to the training set. This leads to excellent training performance, but fails on new data. An overfit model is like a complex curve chasing noise, missing the underlying trend. The performance gap between training and validation sets is a classic symptom. The validation set is our early warning system, helping us combat overfitting through regularization. While overfitting is a major concern, it has an opposite, an equally problematic, twin underfitting. Underfitting occurs when a model is too simple to capture the underlying structure of the data. It fails to learn the relationships between the features and the target variable, even on the training data. An underfit model has not learned enough. It performs poorly, not only on the testing set, but also performs poorly on the training set itself. It's a sign that our chosen model lacks the capacity or complexity to understand the data. Let's go back to our scatterplot of data points. Imagine the true underlying relationship is a distinct curve, like a U-shape. If we try to fit this data using simple linear regression, which can only draw a straight line, the model will fail spectacularly. The straight line will cut across the U-shape, being far away from most of the data points. The model is too simple, too rigid to capture the curve pattern. It will have a high error rate on the training data, and it will also have a high error rate on the testing data. This is a classic case of underfitting. Underfitting is usually easier to detect than overfitting. If your model is performing poorly on the training set, that's a strong indicator that it is underfit. The solution to underfitting is generally to increase the model's complexity. You could try switching from linear regression to polynomial regression to allow for curves. You could allow a decision tree to grow deeper. You could add more informative features to the data through feature engineering. Essentially, you need to give the model more power and flexibility to learn the patterns that it is currently missing. The goal of a machine learning practitioner is to find the sweet spot between underfitting and overfitting. We want a model that is complex enough to capture the true underlying signal in the data, but not so complex that it starts memorizing the noise. This balance is often called the bias-variance trade-off. Underfit models have high bias. They are biased towards being too simple, while overfit models have high variance, meaning their predictions would vary wildly if trained on a different training set. The validation set helps us navigate this trade-off and find a model that generalizes well by striking that perfect balance. The train-validate-test split is a great strategy, but it has one potential weakness. The performance of our model can depend on how the random split was made. By chance, we might end up with a particularly easy or hard validation set, which could mislead us during the model tuning process. This is especially risky when we have a relatively small dataset, as each slice of data becomes quite small. To overcome this and get a more robust estimate of our model's performance, we can use a powerful technique called k-fold cross-validation. Here's how k-fold cross-validation works. Instead of doing a single split into a training and validation set, we split our data, after setting aside the final test set, into k equal size chunks or folds. A common choice for k is 5 or 10. Let's say we choose k equals 5. We now have 5 folds of data. We then run a series of k experiments. In the first experiment, we use fold 1 as our validation set, and train our model on the other 4 folds, folds 2, 3, 4, and 5. We calculate the performance score on fold 1, then we start the second experiment. This time, we use fold 2 as our validation set and train the model on the remaining data, folds 1, 3, 4, and 5. We again calculate the performance score. We repeat this process until every single fold has been used exactly once as the validation set. At the end, we will have k different performance scores, one from each experiment. To get our final performance estimate, we simply average these k scores. This average score is a much more stable and reliable estimate of the model's performance than what we would get from a single train validation split. Cross-validation is a powerful tool for model selection and hyperparameter tuning. We can evaluate different algorithms or different hyperparameter settings by comparing their average cross-validation scores. It gives us more confidence that our chosen model will perform well on unseen data because it has been tested on all parts of our available data. While it is more computationally expensive, we have to train the model k times instead of just once. The resulting robust performance estimate is often well worth the extra effort, especially when working with smaller datasets. Let's zoom out and assemble everything we have learned into a single, coherent workflow. This is the standard, battle-tested procedure that data scientists follow to build and evaluate a supervised learning model responsibly. Following these steps helps ensure that your results are trustworthy and that you have avoided the common pitfalls of overfitting and testing on training data. This workflow provides a clear roadmap from a raw dataset to a final evaluated model. It is the practical application of all the principles we have discussed. First, you begin with your entire dataset. The very first thing you do is split off a final testing set, let's say 15 to 20% of the data, and lock it away in a vault. Do not touch it, look at it, or think about it again until the very end. The remaining 80 to 85% of your data is now your development data. Second, you take this development data and use it for model selection and tuning. You can either do a simple split into a training set and a validation set, or for more robustness, you can use k-fold cross-validation on this entire development set. Third, using your chosen validation strategy, either the single validation set or cross-validation, you experiment with different algorithms and hyperparameters. You train each candidate model on the training portions and evaluate it on the validation portions. You compare their performance scores and select the single algorithm and set of hyperparameters that perform the best. This is your champion model configuration. Fourth, now that you have made your final choice, you take your winning algorithm and train it one last time on the entire development dataset, all the data except the locked-away test set. This ensures your final model learns from as much data as possible. Finally, you reach the last step. You take your fully trained champion model and unlock the vault containing the testing set. You use the model to make predictions on this final unseen data and calculate its performance score. This score is your final, honest estimate of the model's performance in the real world. This rigorous, disciplined process, with its strict separation of data for training, tuning, and final testing, is what separates professional machine learning practice from amateur mistakes. It is the key to building models that truly work. After training, we need to evaluate our final model. Is this model any good? We need performance metrics. The most intuitive metric is accuracy. Accuracy tells us the fraction of correct predictions, but this simplicity can be dangerously misleading, especially with imbalanced datasets. A high accuracy score can hide significant underlying problems. Accuracy gives us no insight into different types of errors. To truly understand our model's behavior, we must look beyond accuracy and use a suite of more nuanced metrics like precision and recall. To move beyond accuracy scores, we need a detailed breakdown of our model's performance. The best tool for this is the confusion matrix, a table that summarizes a classification model's performance, showing where it gets things right and wrong. For a binary classification problem, the confusion matrix is a 2x2 table contrasting the model's predictions with actual labels. It has 4 cells: true positives, TP, true negatives, TN, false positives, FP, and false negatives, FN. The confusion matrix gives us a comprehensive view of our model's behavior, showing the exact number of each type of correct and incorrect prediction. This detail is essential for diagnosing problems and calculating advanced metrics. From the confusion matrix, we calculate precision. Precision measures exactness of all positive predictions, how many were correct. It minimizes false positives. Precision equals true positives divided by true positives plus false positives. Consider a video recommendation model. Low precision means irrelevant videos, annoying users. Or in law, it could mean wasting lawyers' time. High precision reduces the cost of false positives, but focusing only on precision can be misleading. A model could miss most cases. Balance precision with recall for a complete picture. While precision focuses on quality, recall focuses on quantity. Recall, also known as sensitivity, answers. Of all actual positive cases, how many did the model identify? Recall equals true positives divided by the sum of true positives and false negatives. Recall is most important when the cost of a false negative is very high, like in rare disease detection. Consider fraud detection. A false negative means the customer loses money. There is often a trade-off between precision and recall, and the choice depends on the specific business problem. There is an inherent tension between precision and recall. Improving one often comes at the expense of the other. The F1 score combines precision and recall into a single metric. The F1 score is the harmonic mean of precision and recall. It seeks to find a balance between the two. The F1 score is particularly useful when you have an imbalanced class distribution. It is a great default metric for any classification problem when the class distribution is uneven. The F1 score provides a robust way to find a model that performs reasonably well on both fronts. For binary classification, the Rossi curve and AUC are powerful evaluation tools. A ROC curve visualizes a classification model's performance at all possible classification thresholds, plotting the true positive rate against the false positive rate. A good model bows towards the top left. Random guessing is a diagonal line. AUC summarizes the curve. 1 is perfect, and 0.5 is random. AUC is threshold independent and robust for imbalanced datasets. Let's dive into a complete supervised machine learning project. We'll use the Palmer penguins dataset to predict penguin species based on physical measurements. This is a multi-class classification problem involving 3 species: Adelie, chinstrap, and gentoo. We'll use numerical features like bill length and flipper length to train our model. We will cover loading, cleaning, splitting data, choosing an algorithm, training, predicting, and evaluating performance. This walkthrough aims to demystify the process and build your intuition for machine learning. Let's meet the penguins. Before working with penguin data, we need a digital workspace. A data scientist needs software tools. We'll use Python, along with popular libraries for data science and machine learning. First, Pandas, the ultimate spreadsheet tool for Python, perfect for loading, cleaning, and exploring data. Next, scikit-learn or sklearn, the workhorse of our project. It's a user-friendly machine learning library. To run code, we'll use a Jupyter notebook, an interactive environment. It lets you run code in chunks and see the output immediately. A few powerful free libraries are all you need. Our first step in any project is to load our data into our workspace and take a first look at it. This is our first contact with the dataset, where we get a feel for its structure, what features it contains, and whether there are any obvious issues we need to address. Using the pandas library, this is incredibly easy. We can load the data, which is typically stored in a file like a CSV or comma-separated values, with a single line of code. This will create a pandas data frame, our digital table, which we can then inspect. Let's look at the code. We will import the pandas library, and then use its read_CSV function to load the penguin dataset. After loading it, we will use the head method to display the first 5 rows of the table. This is a great way to quickly check if the data loaded correctly and to see what the columns look like. It gives us an immediate snapshot of our features and our target label. So here's the code. Looking at this output, we can see our columns clearly. We have our target variable species, which we want to predict. Then we have our features, bill_length_mm, bill_depth_mm, flipper_length_mm, and body_mass_g. We might also see other columns like island or sex. This initial exploration is also where we would check for missing values. Real-world data is often messy. A penguin might have been weighed, but the bill measurement might have been missed. Pandas gives us easy tools to check for these missing data points, which we will need to handle before we can train our model. Another useful step in this initial exploration phase is to use the info method in pandas. This gives us a concise summary of our data frame. It tells us how many rows we have in total, the name and data type of each column, and how many non-missing values each column contains. This is a quick diagnostic check to understand the overall health of our dataset. Getting to know your data intimately at the beginning of a project is a crucial habit. It helps you anticipate problems and make better decisions in the later stages of the modeling process. Machine learning algorithms are powerful, but they are also picky. They need the data to be in a very specific format. Specifically, they need all the input features to be numerical, and they cannot handle missing values. Our next job is to clean and prepare our data to meet these requirements. This process, often called data pre-processing, is a critical step that ensures our algorithm can understand and learn from the information we provide. For our penguin dataset, this will involve 2 main tasks: handling missing values and converting our target label into numbers. First, let's address missing values. From our initial exploration, we might have noticed that some rows have empty cells for certain measurements. We have a few options for how to deal with this. We could delete any row that has a missing value. This is the simplest approach, but it means we lose some of our precious data. Another common strategy is imputation, where we fill in the missing values with a reasonable substitute, such as the average or mean or median value for that entire column. For this example, let's keep it simple and just drop the few rows that have missing data to ensure our dataset is complete. Second, our target variable, species, is currently text, Adelie, Chinstrap, or Gentoo. Our algorithm needs this to be numerical. We need to encode these strings into numbers. A simple way to do this is to map each species to a unique integer. For example, we could decide that Adelie equals 0, Chinstrap equals 1, and Gentoo equals 2. This process is called label encoding. Scikit-learn has tools to do this automatically, but doing it manually with pandas helps us see exactly what is happening. We are translating our human-readable labels into a language the machine can understand. Finally, we need to separate our data into our features, the inputs, and our target label, the output. We will create one variable, typically called x, which will be a data frame containing only our feature columns, like bill_length_mm and flipper_length_mm. We will create another variable, y, which will contain only our target column, species. This explicit separation into x and y is the standard convention and is what scikit-learn's algorithms expect as their input. With our data now clean, numerical, and properly separated, we are ready for the next crucial step. Okay, now that we have our clean data, neatly separated into our features x and our target y, it's incredibly tempting to just feed all of this data to our model. But as we learned in part 4, this would be a cardinal sin. We really must abide by the golden rule. Never test your model on the data it was trained on. To get an honest assessment of our model's ability to generalize, we have to split our data into a training set and a testing set. The training set will be used to teach the model, and the testing set will be held back as a final exam. Scikit-learn makes this critical step incredibly simple with a function called train_test_split. This function takes our features x and our target y, and shuffles them randomly before splitting them into 4 separate pieces. x_train, which is the features for the training set, x_test, which is the features for the testing set, y_train, which is the labels for the training set, and y_test, the labels for the testing set. We can also specify what proportion of the data should be allocated to the testing set. A common choice is to use 80% for training and 20% for testing. Let's see this in action with code. We will import the function from scikit-learn and then apply it to our x and y data. We'll set the test underscore size to 0.2, meaning 20% of the data will be reserved for the test set. We also often set a random underscore state parameter. This is just a number that ensures that if we run the code again, the random split will be exactly the same. This is very useful for making our results reproducible. After running this single line of code, our data is now properly partitioned. X underscore train and Y underscore train form our classroom material. This is the only data our model will get to see during the learning phase. X underscore test and Y underscore test are locked away in our vault. The features in X underscore test will be used to generate predictions, and the true labels in Y underscore test will be used to score those predictions and give our model its final grade. This discipline separation is the absolute foundation of building a trustworthy machine learning model. It is a non-negotiable step in the workflow, and scikit-learn makes it honestly painless to implement correctly. The moment has arrived. With our data prepared and split, it is time to choose an algorithm and train our model. This is the learning part of machine learning. For our penguin species classification problem, there are several good algorithms we could choose from our scikit-learn toolbox. We could use a decision tree, a support vector machine, or a random forest. As we discussed, a random forest is often a very strong performer because it is an ensemble of many decision trees and is resistant to overfitting. Let's choose the random forest for our mission. The process in scikit-learn is beautifully consistent and follows a simple pattern. First, import the model class you want to use. Second, create an instance of the model, which is like creating a blank untrained version of it. Third, fit the model to the training data. The .fit method is the magic command that triggers the entire learning process. It takes the training features, x underscore train, and the training labels, y underscore train, as input and runs the algorithm to learn the mapping between them. Here is what the code looks like. We import the random forest classifier from scikit-learn. We create an instance of it, which we will call model. We can set hyperparameters here, like the number of trees in the forest, but we will stick with the defaults for now. Then, we call the fit method on our model, feeding it our training data. After this line of code executes, our model variable is no longer a blank slate. It is a fully trained model that has learned the patterns from our penguin data. That's it. With just these 3 lines of code, we have trained a sophisticated machine learning model. The model.fit command did all the heavy lifting behind the scenes. It built hundreds of individual decision trees, each on a random sample of the data and features, just as we discussed in part 3. The complex logic for how to distinguish between an Adelie, chinstrap, and Gentoo penguin based on their measurements is now encapsulated within our model object. It is ready and waiting to be tested on new data it has never seen before. This simple import, instantiate, fit pattern is the core of training any model in scikit-learn. Our model is now trained and holds all the knowledge it has learned from the training data. The next logical step is to use this knowledge to make predictions on new data. The ultimate test of our model is its performance on the testing set, which we have carefully kept separate and unseen until now. We will take the features from our testing set, x underscore test, and feed them to our trained model. For each penguin in the test set, the model will look at its measurements and predict which of the 3 species it thinks it belongs to. The process for making predictions in scikit-learn is just as simple as the training process. Every trained model has a predict method. This method takes one argument, a set of input features for which you want to generate predictions. In our case, we will pass it x underscore test. The model will then go through each row in x underscore test, apply the complex logic it learned during training, and output its best guess for the species. The result will be an array of predictions, one for each of the penguins in our test set. Let's look at the code. It is a single intuitive line. We call the .predict method on our trained model object, passing x underscore test as the input. We will store the results in a new variable called y underscore pred, which stands for predicted y values. This y underscore pred variable will now contain our model's best guesses for the species of the penguins in our test set. After running this code, we have our predictions. We can even print out the first few predicted values and compare them side by side with the true labels from y underscore test. This gives us a quick anecdotal check to see if the model seems to be on the right track. For example, if the true labels for the first 5 test penguins were Adelie, Gentoo, chinstrap, Adderley, and our model predicted the same. That is a great sign. But to get a rigorous quantitative measure of its performance, we cannot just look at a few examples. We need to systematically compare all of our predictions in y_pred against all of the true labels in I_test. We have our predictions, y_pred, and the ground truth, y_test. Now, it is time to grade our model's final exam. How well did it actually do? This is where the evaluation metrics we discussed come into play. We really need to move beyond just looking at a few examples and calculate formal metrics that summarize the model's performance across the entire test set. Scikit-learn provides easy-to-use functions for key metrics, including accuracy and the confusion matrix. The accuracy_score function takes the true labels, y_test, and our model's predicted labels, y_pred, and calculates the fraction of predictions that were correct. While accuracy is useful, the confusion matrix gives us a much deeper insight into what kind of mistakes our model is making. By looking at the confusion matrix, we can see exactly where the model got confused, completing our evaluation of the model we built. Numbers and tables like the confusion matrix are powerful, but sometimes a picture is worth 1,000 numbers. Visualizing our model's results can give us an even more intuitive understanding of its performance and behavior. A great way to visualize a confusion matrix is to plot it as a heat map. A heat map uses color intensity to represent the numbers in the grid. This makes it very easy to see at a glance where the largest numbers are, both the correct predictions on the diagonal and any significant errors off the diagonal. We can create this visualization using Python libraries like Matplotlib and Seaborn. We would take the confusion matrix we generated in the previous step and pass it to a heat map plotting function. We can add labels to the axes to show the names of the penguin species, making the plot easy to interpret. The diagonal cells, representing correct classifications, will typically have the darkest or brightest colors, while the off-diagonal error cells will be much lighter. This immediately draws our eyes to the model's successes and failures. Another powerful visualization is to plot the decision boundaries of our model. For a model with only 2 features, we could create a scatter plot of the test data, coloring each point by its true species. Then, we can overlay the regions where our model would predict each species. This shows us the lines or curves the model has drawn in the feature space to separate the classes. It gives us a literal picture of the model's mind, showing us the rules it has learned in a geometric way. This helps us understand if the model has learned a simple, sensible boundary or a complex, potentially overfit one. This final step of visualization really closes the loop on our project. We started with raw data, we cleaned it, we trained a model, we evaluated it with numbers, and now we have visualized its performance in an intuitive way. This end-to-end process, from loading a CSV file to plotting a final graph, encapsulates the entire practical journey of a supervised machine learning project. You have now seen how all the theoretical pieces fit together to create a tangible, working model that can make intelligent predictions about the world. You are well on your way to unlocking the power of supervised learning. We have traveled a great distance together on this learning adventure. Let us take a moment to look back at the path we have covered. We began with a simple question: what is supervised machine learning? We discovered it is the art and science of teaching a computer by showing it examples. Instead of writing rigid rules, we provide data with clear labels, and we ask the machine to figure out the rules for itself. We learned that this simple idea is the engine behind countless modern technologies, from the spam filter in your inbox to the recommendation engine that suggests your next favorite movie. It is all about making predictions based on past experience. We then dove into data. We saw that data is not just a collection of numbers. It is a structured representation of the world. We explored the 2 main flavors of supervised learning classification, which is about sorting things into categories, and regression, which is about predicting a numerical value. With our understanding of data established, we opened the algorithmic toolbox and met linear regression, decision trees, and support vector machines. This gives us the power to choose the right tool for the right job. Finally, we brought it all together with the practical side of the craft. We learned the golden rule of splitting our data into training, validation, and testing sets to get an honest measure of performance. We armed ourselves with a suite of evaluation metrics beyond simple accuracy, like precision, recall, and the F1 score. And we walked through a complete hands-on example, predicting the species of penguins. This journey has equipped you with a complete foundational understanding of the supervised learning workflow. The core philosophy of supervised machine learning is letting the data speak for itself. This is a shift from traditional programming, where human logic was hard-coded into the system. Supervised learning admits that we often don't know the best rules. We provide examples and a learning framework, but let the machine discover connections. Focus shifts from writing logic to curating data and asking the right questions. Is the data clean, representative, and unbiased? This data-centric view is key. Immerse yourself in the data, prepare the data so it can tell its story. Beyond the technical skills, building successful machine learning models requires cultivating a specific mindset. This mindset is a blend of three key qualities: boundless curiosity, healthy skepticism, and rigorous discipline. These are the intangible skills that separate a good practitioner from a great one. They guide you through the complexities of a project, help you avoid common pitfalls, and ultimately lead you to build models that are not just technically correct, but also genuinely useful and reliable in the real world. Let's explore each of these essential traits. First and foremost, you must be driven by curiosity. This is the engine of all discovery. A curious practitioner is constantly asking questions. Why did the model make that mistake? What would happen if I created a new feature that combines these two old ones? What other data sources could I bring in to enrich my model? This curiosity pushes you to go beyond the default settings, to experiment with different approaches, and to dig deeper into your data to understand its nuances. It transforms the process from a mechanical task into a fascinating investigation, a puzzle waiting to be solved. Second, you must maintain a healthy dose of skepticism, especially about your own results. It is very easy to fall in love with a model that produces a high accuracy score. A skeptic, however, always asks, is this score too good to be true? They question everything. Did I accidentally leak data from my test set into my training set? Is my evaluation metric hiding a serious problem, like in the case of an imbalanced dataset? Is this model simply memorizing the data rather than learning from it? This skepticism is your primary defense against fooling yourself and building models that fail silently when deployed. Finally, you must practice rigorous discipline. Machine learning is not magic. It is a scientific and engineering process. Discipline means following the established best practices, even when it feels tedious. It means always splitting your data correctly, never peeking at the test set until the very end, and documenting your experiments so you can reproduce your results. It means being honest about your model's limitations and transparent about its potential biases. This discipline ensures that your work is reliable, trustworthy, and stands up to scrutiny. It is the foundation upon which robust and responsible AI is built. The path of a machine learning practitioner is filled with potential pitfalls. Being aware of these mistakes is the first step toward avoiding them. Think of this as a friendly warning. Many a promising project has been derailed by simple errors. By learning to recognize them, you can save yourself countless hours of frustration. Let us highlight a few of the most common mistakes to watch out for, like leaking data. The most common form of this is testing your model on the data it was trained on. This gives you a completely false sense of confidence. Always split your data first before doing anything else. Another common mistake is choosing the wrong evaluation metric for your problem. Matching your metric to your mission is absolutely crucial for success. A third pitfall is ignoring the importance of feature engineering. Be wary of these traps and you will be well on your way. Beyond avoiding mistakes, there are habits and expert tips that can elevate your machine learning practice. These are the small things that, when done consistently, compound over time to give you a significant edge. First, start simple, then iterate. Start with the simplest possible model, often called a baseline. Second, become one with your data. Spend real time exploring it and create visualizations. Finally, embrace the principle of Occam's razor. A simpler model is better than a more complex one. As we build predictive models, we must accept the responsibility that comes with it. These models impact people's lives, influencing loans, jobs, healthcare, and even sentences. We must consider the ethical dimensions of our work. The most pressing challenge is bias. Models learn from data, amplifying existing societal biases. A hiring model can learn to be a biased recruiter itself. Building responsible AI requires vigilance in identifying and mitigating bias. Another key consideration is transparency. Many models operate like black boxes, making it hard to understand their decisions. In healthcare or criminal justice, this is unacceptable. Explainable AI develops techniques to make decision-making more transparent. Building responsible AI is everyone's duty, requiring us to ask difficult questions and ensure our technology serves humanity justly. Congratulations on completing this foundational journey into supervised machine learning. You have built a solid, intuitive understanding of the core concepts, the key algorithms, and the practical workflow. But as with any great adventure, reaching the summit of one peak only reveals the vast mountain range that lies beyond. This is just the beginning of your learning path. The field of machine learning is vast and constantly evolving, offering a lifetime of fascinating topics to explore. So what are some logical next steps you could take from here? One excellent path is to deepen your practical skills. The best way to solidify your knowledge is to apply it. Find your own datasets and try to build your own models. Websites like Kaggle offer a huge collection of datasets and host competitions that are a fantastic way to practice on real-world problems. Start a personal project that interests you. Can you predict the price of a used car? Can you classify different types of flowers? The more you practice the end-to-end workflow, from data cleaning to model evaluation, the more confident and proficient you will become. There is no substitute for hands-on experience. Another path is to go deeper into the theory. In this course, we focused on intuition over mathematical formalism. If you enjoyed the why, you might now be ready to dig into the how in more detail. You could explore the linear algebra, calculus, and probability theory that underpin these algorithms. Understanding the mathematics will give you a more profound appreciation for how these models work and will empower you to read academic papers and understand the very latest research. This theoretical foundation is what allows you to move from being a user of algorithms to becoming a creator of new ones. Finally, you can begin to explore the other major branches of machine learning. We have focused exclusively on supervised learning. You could now venture into unsupervised learning, where the goal is to find hidden structures in unlabeled data using techniques like clustering. Or you could dive into the exciting world of deep learning and neural networks, the technology behind recent breakthroughs in image recognition and natural language processing. The foundations you have built here will serve you well, as many of the core principles apply across all areas of machine learning. The choice is yours, and the adventure awaits. We have reached the end of our structured course, but we are at the true beginning of your personal journey with machine learning. The goal of these lessons was never to teach you everything there is to know. That would be an impossible task. Instead, the goal was to give you a map, a compass, and the confidence to take your first steps into a new and exciting world. It was about demystifying a subject that can often seem intimidating and revealing the simple, elegant ideas that lie at its core. It was about empowering you to see the world through the lens of data and prediction. The skills and concepts you have learned here are more than just a technical toolkit. They represent a new way of thinking. You will start to see patterns and potential prediction problems everywhere. When you read the news, you might think about the data that could be used to forecast economic trends. When you use a streaming service, you will appreciate the complex classification models working behind the scenes. This new perspective is a powerful one. It allows you to engage with the technology shaping our future, not as a passive consumer, but as an informed and critical thinker. Never lose the sense of wonder you felt when these ideas first started to click. The ability for a machine to learn from experience, to find patterns that no human has ever seen, is a truly remarkable thing. It is a field that blends creativity, science, and a deep understanding of data. It is constantly changing, with new discoveries being made every day. Your journey will be one of continuous learning, and that is what makes it so rewarding. Stay curious, stay skeptical, stay disciplined, and never stop asking questions. Thank you for joining me on this exploration. I hope you have found it as illuminating and exciting as I have. You are now equipped with the foundational knowledge to understand, build, and critique supervised machine learning models. The power to turn data into insight is now in your hands. Go forth, explore the vast data sets of the world, and build things that are not only intelligent, but also responsible, fair, and beneficial to all. The adventure is just beginning. If you enjoyed this course, please like, share, and subscribe for more content on machine learning and data science. Stay curious and